What if the universe never ends, and never began? Think about that for a moment. It's a question that tickles the mind, isn't it? We are so used to beginnings and endings in our daily lives. Stories start and finish. Days dawn and then dusk arrives. Our own lives have a start and eventually an end. So it's natural to think the universe must be the same, but what if it isn't? What if the cosmos just is? This idea challenges everything we think we know. Imagine a place with no before the start. Imagine a space with no beyond the edge. It's a concept that astronomers and physicists grapple with. It is a deep, profound mystery. We look up at the night sky, filled with countless stars, and we wonder about the grand scale of it all. Is there a wall somewhere out there? Or does it just keep going? The quest to understand the universe's nature is ancient. Humans have always looked to the heavens. We've always asked these big questions. Today, we use powerful telescopes and complex mathematics. Yet, the fundamental questions often remain. So let's embark on this journey together. When we talk about the universe, we often mean two different things. First, there's the observable universe. This is the part of the cosmos we can actually see. It's everything whose light has had time to reach us. Light travels incredibly fast, but space is incredibly vast. The universe is about 13.8 billion years old, so light from the most distant objects has traveled for 13.8 billion years to reach our telescopes. This creates a sort of cosmic bubble around us. This bubble is our window to the cosmos. It's huge, about 93 billion light-years across. Why bigger than 13.8 billion light-years? Because the universe has been expanding. While light traveled, the space it crossed was also stretching. So, the source of that ancient light is now much farther away. Everything inside this sphere is, in principle, visible to us. We can study its galaxies, its stars, its ancient light. But here's the crucial part. Our observable universe has an edge. This edge isn't a physical wall or a barrier, it's an information horizon. It's the limit of what we see for now. Light from beyond this boundary simply hasn't had enough time to reach Earth. So, what about the actual universe? This is the entirety of space and time. It includes everything that exists, has existed, and will exist. It's the whole cosmic shebang, not just the part we can see. Is this actual universe bigger than our observable part? Most astronomers think so. In fact, it could be vastly, unimaginably larger. It might even be infinite. That's a mind-bending thought, isn't it? Imagine our observable universe as a tiny grain of sand. The actual universe could be an entire beach, or an entire desert, or perhaps a desert that never, ever ends. We don't have direct evidence of what's beyond our light horizon, but our theories, like cosmic inflation, suggest it's vast. Inflation proposes an incredibly rapid expansion in the first tiny fraction of a second. This would have stretched the universe far beyond what we can observe today. The idea of an actual universe much larger than our observable one is profound. It means there could be countless other regions out there, regions with their own galaxies, stars, and maybe even life. Let's talk about space itself. Can space be finite, or must it be infinite? If the universe has no edge, does that automatically mean it's infinite? Not necessarily. This is where things get a little tricky, but also very cool. Think about the surface of the Earth. You can travel in any direction on Earth's surface, you'll never fall off an edge, you'll never hit a "you are here" sign marking the end. Yet, the surface of the Earth is finite. It has a limited area. How is this possible? Because the Earth's surface is curved. It's a two-dimensional surface curved into a third dimension. So, it's finite, but unbounded. You can walk forever and never find an edge, eventually returning to your starting point. Could the universe be like that? Could our three-dimensional space be curved in a similar way? Curved into some higher unseen dimension? This is a mind-stretching idea, but it's a real possibility in cosmology. So, we have two main possibilities for the universe's spatial extent. It could be truly infinite, stretching on forever in all directions without limit, an endless ocean of stars and galaxies, or it could be finite but unbounded, like the surface of a sphere but in 3 dimensions. Section 5, Einstein's cosmic fabric, the curvature of space-time. To really understand these ideas of finite and infinite space, we need Albert Einstein. His theory of general relativity revolutionized how we see gravity. Before Einstein, we thought of gravity as a force, a mysterious pull between objects with mass. But Einstein had a different idea. He said gravity isn't a force pulling things through space. Instead, gravity is the curvature of space-time itself. That's a big leap in thinking. Imagine space-time as a giant, flexible fabric, like a trampoline. If you place a heavy object like a bowling ball onto this fabric, what happens? The fabric bends, it curves, it warps around the bowling ball. Now if you roll a marble nearby, it won't travel in a straight line. It will curve inwards, towards the bowling ball. Not because the bowling ball is pulling it, but because the fabric of space-time itself is curved by the bowling ball's mass. This is how Einstein explained gravity. Planets orbit stars not because of a direct pull, they orbit because they are following the curves in space-time. Curves created by the star's mass and energy. Section 6, Cosmic Shapes, the closed universe, a cosmic sphere. If the universe has enough mass and energy, enough stuff in it, then space-time could curve back on itself. This would create what we call a closed universe. Think again about the surface of a sphere. It's a two-dimensional analogy for a three-dimensional closed universe. In such a universe, space is finite, but unbounded. You could fly your spaceship in one direction, and after an unimaginable amount of time, you'd arrive back where you started. No edge, just a cosmic round trip. A closed universe has positive curvature, like a sphere. Imagine drawing a giant triangle in this kind of space. The angles of your triangle would add up to more than 180 degrees. Parallel lines, if extended far enough, would eventually meet. This is very different from the geometry we learn in school. That Euclidean geometry describes flat space. But in a closed universe, space itself is curved. It's a self-contained cosmos. What would this mean for the universe's fate? A closed universe, with its high density, has strong gravity. This gravity would eventually overcome the universe's expansion. The expansion, which we see happening now, would slow down, it would stop, and then it would reverse. The universe would begin to contract. Section 7, Cosmic Shapes, the open universe, an endless saddle. What if there isn't enough mass and energy in the universe? What if the density is too low to curve space back on itself? In that case, we might live in an open universe. This type of universe has negative curvature. Imagine the shape of a saddle or a Pringles potato chip. That's a two-dimensional surface with negative curvature. An open universe would be the three-dimensional equivalent. It would extend infinitely in all directions. In an open, negatively curved universe, geometry is also different. If you drew a giant triangle, its angles would add up to less than 180 degrees. Parallel lines would diverge, getting farther and farther apart. This kind of universe is infinite in spatial extent. It goes on forever. There's no coming back to your starting point if you travel in a straight line. You just keep going, and going, and going, into an endless cosmic expanse. What about the fate of an open universe? With not enough matter to halt its expansion, it would expand forever. Galaxies would continue to move farther apart, the universe would become colder and darker over eons, stars would eventually burn out. Section 8, Cosmic Shapes, the flat universe, a never-ending plane. There's a third possibility, sitting right between the closed and open models. This is the flat universe. In this scenario, the universe has just the right amount of mass and energy. This is called the critical density. If the density is exactly critical, then space-time has zero overall curvature. It's flat, like a perfectly smooth infinite sheet of paper in our two-dimensional analogy, or an infinitely extending three-dimensional space. This is the kind of geometry we're most familiar with. In a flat universe, the rules of Euclidean geometry apply on the largest scales. The angles of a giant triangle would add up to exactly 180 degrees. Parallel lines would remain parallel forever. They would never meet and never diverge. Like an open universe, a flat universe is also spatially infinite. It stretches on without end. There's no edge and no cosmic return journey. Just endless space, in every direction you look. What's the fate of a flat universe? It also expands forever, much like an open universe. However, the rate of expansion is finely balanced. Section 9, Living in Infinity, Time, Expansion, and Our Place. So if our universe is indeed flat or perhaps open, it means it's likely infinite. What does an unbounded, infinite universe mean for us? For time, for expansion, for our very existence? It's a lot to take in. If space is infinite, then out there, beyond our observable horizon, there's more universe. Potentially an infinite amount more. This means an infinite number of galaxies, stars, and planets. An infinite number of chances for things to happen. Consider the implications for time. An infinitely expanding universe suggests time itself will also go on forever. There's no big crunch to end things. The cosmic clock just keeps ticking. The universe continues to evolve, to change, to become more diffuse. Our current era with its bright stars and clustered galaxies is just a fleeting moment. A tiny slice in an infinitely long cosmic history. It's a humbling perspective on our place in the grand scheme of things. The ongoing expansion is a key feature of this unbounded reality. We see galaxies rushing away from us. The farther they are, the faster they recede. This isn't because we're at the center of an explosion, it's because space itself is stretching everywhere.